Welcome. So previously we learned how to determine if functions defined by tables and graphs have corresponding inverse functions. In this video, we'll learn how to determine if functions defined by formulas have corresponding inverse functions. But before we jump in, let's quickly review a few key ideas about functions and properties of inverse functions. So we know a function is a repeatable process that takes a collection of input values and generates a corresponding collection of output values with the key property that if we use a particular single input, the process always produces exactly the same single output. So every input corresponds to exactly one output, guarantees that we have a function. We can determine whether or not a given function f has a corresponding inverse function by determining if the process that defines f can be reversed so that we can also think of the outputs as a function of the inputs. So does every output correspond to exactly one input? If so, then we could have an inverse function. We know that if y equals f of t, then we can express the exact same relationship from a different perspective by writing t equals f inverse of y. To find the inverse function f, we will reverse the process by solving for the input variable. So notice that if t is the input of function f, t will become the output of f inverse. And since y was the output of function f, y will become the input of f inverse. And then we'll determine if this new formula guarantees that each y value corresponds to one and only one t value. So determine with justification whether functions f and g have corresponding inverse functions. So as previously stated, to determine if f has an inverse function, we will reverse the process of f by solving for the input variable x. So let's write this as y equals 2/3 x minus 1 squared plus 4. It's important to note we are not going to switch x and y as you may have learned in previous courses. We are simply going to solve for x. So first we'll reverse adding 4 by subtracting 4 on both sides to get y minus 4 equals 2/3 x minus 1 squared. Then we'll multiply both sides by 3/2 to reverse the 2/3 multiplication. That results in 3/2 times the quantity y minus 4 equals the quantity x minus 1 squared. Next, we take the square root of both sides. Remember that squaring a positive or a negative number always results in a positive number. So thus, when we take the square root of both sides, the result could be a positive or a negative square root of 3/2 times the quantity y minus 4, and that will equal x minus 1. Lastly, add 1 to both sides, and we get 1 plus the square root of 3/2 y minus 4, or we get 1 minus the square root of 3/2 times y minus 4. So notice that for any given y value, x can be expressed two ways. X equals 1 plus the square root of 3/2 y minus 4, and x could equal 1 minus the square root of 3/2 y minus 4. So x could take on two different values given one value, y value. And as a result, x is not a function of y. So that actually tells us that this function f does not have an inverse function. So now let's see if function g has an inverse function. We'll rewrite the formula as y equals 2/3 times x minus 1 plus 4. Again, it's important to note we're not going to switch x and y. We're just going to solve for x. And hopefully it'll be clear why when we're done. So we're going to subtract 4 from both sides. We'll get y minus 4 equals 2/3 times x minus 1. And then multiply both sides by 3/2. So 3/2 times y minus 4 equals x minus 1. And lastly, add 1 to both sides. So x equals 1 plus 3/2 times the quantity y minus 4. Here we see that given any y value, there will be one and only one corresponding x value. That means that x is a function of y, and so g has an inverse function. Since g has an inverse function, it would make sense to write that x equals g inverse of y, which equaled 1 plus 3/2 y minus 4. So when we write it this way, it might become clearer why we did not switch x and y to start. We know that if y equals g of x and g has an inverse, then we can write x equals g inverse of y. By solving for x immediately, rather than switching x and y, we were able to find a new formula for x, where x is now the output and y is the input. Exactly what we wanted to find for an inverse function.